Hey everyone, this video is about the Casio fx-61F electric formula calculator from 1988. And the 61F is another Casio calculator that has obtained a type of cult status and has become very highly sought after, because not only is it quite rare, but as far as I know it's the only calculator ever made that was designed specifically for electronics engineers. Not only has it a unique impedance mode for AC circuit analysis that uses keys like this parallel symbol, but it also has 27 built-in formulae for electronics applications, and it's even programmable as well. And it was all packaged in a beautiful compact form factor with solar power. And 61F was a niche variant of the fx-50F, a more general purpose engineer's calculator, and these two share a lot of their basic functionality. The 50F product line continues to this day with the 50F2 and the 50F2 Plus, but the others in that line are not, in my opinion, as special as the 61F. So let's look at it in detail. Physically, the 61F is a beautiful calculator. Maybe there's a nostalgia factor kicking in for me, but if you've watched my channel a lot, you'll know that I have a thing for Casio calculators from the late 80s. And like other Casio calculators from this era, the 61F is super light and compact. This symbol on the top right is the logo for Casio's C-Power system, which consists of this 3-volt solar cell as well as an internal 1.5-volt GR927 lithium battery. And like with modern Casio calculators such as the 991EX, the intention was that the 61F can operate in the dark without solar power. But in the case of this particular 61F, the GR927 is dead. So if I cover the solar cell, the display powers off. And interestingly, in the user manual, Casio states that although the battery should be replaced at least once every 7 years, this should only be done by a dealer. I'm not sure what the reason for this was specifically, other than it requires the back panel to be removed. Another interesting quirk of the 61F is that, like this 50F, it doesn't actually have an off key, but its power does trigger off after 6 minutes of inactivity. And again, I don't know why Casio designed it this way. If you know or have a theory, let me know in the comments below. And 61F has an interesting hybrid display. It's primarily fairly standard 8-segment section LCD that supports 10 digits mantis and 2 digits exponent, but there's also a small dot matrix section on the left of the screen which displays variable names for formula entry. And the keyboard of the 61F is the typical rubber Casio keys, and although they're not particularly satisfying to press, they tend to be quite reliable. And you can see the usual mode key, and the primary function of many of the other keys depends on the mode. The upper section of the keyboard is really well set up for engineers, so there's an engineering key that allows shifts the display value 3 decimal places to the right, or 3 decimal places to the left if you use the shift key. And there are the usual basic scientific and trig functions. But the most interesting section of the keyboard is in the third row that has this subtle blue background. The primary symbols on these keys correspond to their function in impedance mode, and I'll talk more about these in detail later. The other key whose function might not be obvious is this triangle symbol, which has a dual function. So during number entry, it acts as a backspace, and in impedance mode it switches between the real and imaginary parts of a complex number. On the main keypad, there are some secondary functions related to programming and also SI prefixes. So we have milli, kilo, mega, pico, nano, and micro, and these are handy shortcuts for entering appropriate exponent values. So I'm not going to take this 61F apart today, but here are the internals courtesy of a teardown done by Jose Mesquita. And you can see that the circuitry is fairly simple. There's a battery compartment in circuit with a solar cell powering the PCB, and all the logic is in a single Hitachi system on a chip. And the 61F supports 30 steps of program memory and 14 internal registers. And so I'll skip over talking about the 61F's basic usage because it's very similar to other ADO Casio's calculators I've covered. And we'll jump straight into impedance mode 2. And Casio really could have called this complex mode because complex arithmetic underlies all of its functionality. So in electronics, the imaginary part of a complex number is often denoted with a J to avoid using the I symbol, which usually refers to current. And so let's enter 1 plus 2J. Now if we hit equals, we can use the triangle symbol to switch between the real and imaginary components. And we'll multiply that by another complex number. And one thing to remember with the 61F is that we need to put the second number in brackets. So let's multiply by 3 plus 4J. So times open bracket 3 plus 4J close bracket equals. And so that's negative 5 plus 10J, which sounds right. And so whenever a calculator has complex number functionality, I'm always interested in how well integrated it is. And usually my first test is to take the square root of negative 1, which should be J. And so that's not supported, nor are complex powers. And also trig operations on complex numbers are not supported either, which is a little bit surprising because the 61F does support hyperbolic trig operations, and you can easily write a program yourself to implement complex sign using this formula. And so the complex number functionality on the 61F is fairly shallow. It really only supports basic complex arithmetic. But the most unique feature of the 61F is its ability to calculate the combined impedance of a circuit. And impedance is the name for the resistance of passive components in an alternating current circuit. And just as a refresher, here are the 3 common types of passive components that affect impedance. So there's regular resistors that cause current changes in phase with the current. There's capacitors that store charge in an electromagnetic field and cause current changes that lag the current by 90 degrees. And we also have inductors that store energy in a magnetic field and cause current change that leads the voltage by 90 degrees. And so impedance values are represented by complex numbers because they're effectively vectors. And so when we're doing an impedance calculation, we are typically adding complex values together. So let's look at the example of a resistor, a capacitor, and an inductor connected in series. So to calculate the combined impedance, we first need to start by entering the frequency of the power in our circuit. So in Australia and New Zealand, we use 50 Hertz power. So let's enter that and we hit the FN button. And now all we need to do is to sum the 3 components. So the resistance is 4 kilo ohms. So let's enter 4 and hit the kilo key. And that's left as a real number, 4,000. And then we can add our capacitor value. So that's 20 microfarads, so 20 micro. And then we hit the capacitor key to turn that into its complex term. And lastly, we'll add our inductor value. So that's 0.01 of a Henry, and we'll hit the coil key to get the complex term. And lastly, we hit equals to see the total impedance, and the result is a complex number, so the real component is 4,000 and the imaginary component is a little bit less than minus 156. And we can hit the magnitude key to see the magnitude of the result. So that's around 4003 ohms. And so under the hood, this is the formula that is being calculated. The serial impedance is the sum of the resistance, which is left as a real value, and the capacitance and the inductance values are converted into complex terms through the standard formula. And these terms get evaluated when you hit the capacitance and inductor keys. And these both use a variable omega, which is the angular frequency, which is the power hertz multiplied by 2 pi radians. And if we just want to see what the angular frequency for 50 hertz is, we can hit this button here. So that's around 314 radians per second. So here's a more complex example of a mixed circuit. There's a capacitor C1 in series with a parallel circuit consisting of a resistor and a second capacitor, all in parallel with an inductor. And just to show you how quick it is, I'll quickly enter this and calculate the combined impedance. So again, our circuit frequency is 50 hertz. So we've got a 10 microfarad capacitor, and then that's in series with a 2 kilo ohm resistor plus a 30 microfarad capacitor. And those are in parallel with a 0.006 Henry inductor. And so the result is 1.77 times 10 to the minus 3, and then the imaginary part is around minus 316J. And the magnitude is about 316.42 ohms. And you can see here the calculation that the 61F is doing here under the hood. And so impedance mode on the 61Fs saves a lot of manual drudgery and makes impedance calculations really intuitive, but there's nothing really magic going on. If you have a programmable calculator that supports complex arithmetic, it's fairly straightforward to recreate the functionality. So just quickly, here's some code I wrote for the HP42S, which came on the market in the same year in 1988. And I've made some small keystroke programs that act like the buttons on the 61F. So there's an if-in program which converts our alternating current hertz value to radians per second and stores it in a variable AF for angular frequency. And then there are 3 functions that correspond to the parallel inductor and capacitor buttons. And so let's quickly do that same calculation. So we have a 10 microfarad capacitor that is in series with a 2 kilo ohm resistor plus a 30 microfarad capacitor. So we add those together, and then those two are in parallel with a 0.006 Henry inductor parallel, and then we add those. And so that's the same result as on the 61F. And one additional nice thing about the 42S is it's got better or deeper integration of complex number functionality. So for example, I can take the square root of -1 and get I, and also do a sign on that. The 61F also supports 3 other useful features I'll highlight, and the first is that it supports a formula library of 27 equations related to electronics, and you can pause the video here if you'd like to read through what they are. I'll walk through the example formula 11, the voltage gain of an amplifier circuit. So to use it, we just type in 11 and hit the formula key. We're prompted for our output voltage, so let's enter 30 volts. And now we're prompted for our input voltage, so we'll enter 12 volts. And so the voltage gain is around 7.96 decibels. 61F also supports a very simple programming model, so let's just implement my standard example of the full distance equation. The distance an object falls under gravity in time t. So to record the program, we need to switch to learn mode using mode exponent. And now we can hit the enter key to prompt for our time t, and we'll square that and multiply it by 4.9 and hit equals. And now we need to hit halt to terminate the program. And so we'll switch to run mode now, mode dot, and we can hit run to run the program. So we'll enter, let's say, 10 seconds as our time, and so the object falls 490 meters. And you can only record a single program on the 61F. You cannot view or edit it, and only simple Boolean logic and looping to the start of the program is supported. So again, the feature is fairly limited, but it does support switching modes. So for example, you can use it to streamline calculations in impedance mode. The 61F also has a simple base N mode, which might be useful if you're working with digital electronics. So we can enter base N mode using mode 1, and now we can type in a number, say in hex, and convert it to decimal, binary, or octal. And we can do basic arithmetic, but there are no logical operations supported. And so in summary, the 61F is a really interesting and unique calculator, and it really deserves its cult status. Although it's true we can replicate a lot of its functionality on a general purpose programmable scientific calculator, it's not quite as elegant and intuitive to use. And in that way it reminds me of the HP16C programmer's calculator, another very unique device designed for a niche professional audience. Another interesting aspect of the 61F was that it was the only Casio calculator from the 80s that I know of to support complex arithmetic. Even Casio's advanced scientifics like the 4000P and 4500P didn't have a complex mode. So Casio seemed to have made a decision that complex numbers were mostly useful for electronics engineers. But again, probably the most remarkable thing about the 61F is that Casio and other calculator manufacturers never made a similar calculator since. And so I think it's really quite a special device, and I was really happy to find one. So I hope you've enjoyed the video and found it useful. And if you have, please don't forget to subscribe to the channel and hit the notification bell to get alerted of new videos.